This conference will now be recorded. This conference will now be recorded.
Yeah. Okay. So am I audible, guys? Can you hear me? Okay. So as I was saying, right, that our objective over here had been to understand the macroeconomic modeling, right, and how is it that linear regression gets involved into this macroeconomic modeling, right? So generally, what we have seen of linear regression as a modeling framework is that linear regression is used as it's a cross-section modeling methodology, right? Now, one thing that we wanted to look into over here to understand it is that if we are trying to develop this model, so if we are trying to develop a CCAR model, a stress testing model, then what we need to do is we need to identify each of the components in the P&L statement and in the balance sheet as a function of the macroeconomic variables, right? So that is something that we really want to do. Now to do this, now if you think about it, then there is a macroeconomic dependent variable, which is your, let's say, some of the fee income, or let's say it is interest income and so on, and that there are macroeconomic variables which is impacting the development of these or which is impacting the each of these components, right? So for example, I want to predict the loss uh, that a particular portfolio can be earning. So in that case, I would not only require the historical values of the losses, but also what I would require is the macroeconomic variable. How is it that the macroeconomic variables would drive that particular loss variable? So similarly over here, what we want to understand is how is it that the interest income is impacted by the movement of the macroeconomic variables. And in the last session, what we started talking about was we started talking about some important nuances on macroeconomic variables. We talked about, say, given that there is a GDP series, we wanted to understand that how is it that this GDP series, so how is it that I could incorporate this model or this macroeconomic variable into my model. Now, to incorporate a macroeconomic variable into the model, in any macroeconomic model, we need to understand three things. Number one is whether the variable is stationary or not. Now, when I talk about stationarity, what I mean is that is it that the fundamental or the long run average behavior of the variable which has been incorporated, or is it that there are certain temporary fluctuations in the variable which has also been incorporated? Now, these temporary fluctuations is something which we do not really want in the macroeconomic variable. And when you treat for these temporary trends, say cyclicality, temporary trends, temporary cyclicality, and so on, then what we get is a stationary macroeconomic variable. So the first instance is to ensure that the macro variable that we are using is stationary. That is, it is the average behavior, the average permanent behavior of the variable which is considered for the model development, and that there are no temporary impacts involved. Average permanent behavior. Now, once I have chosen, I have seen that the macro variables are, so I have, once I've selected upon the list of stationary macroeconomic variables, or once I have considered all the macro variables and I have converted them into stationary series, the next question is that out of these variables, how many variables have a long run association? And that is where the concept of co-integration tests come in. Right, so what I need to know is the long run behavior. So whether there is a long run association amongst the variables, and if there is a long run association among two variables, then which is the one which is impacting? So how is the causality, like does the causality operate on both the sides? So this is the causality. So this is the causality, right? So these are the three checks that you need to do, and along with this there is one more check that we need to do. So once we have identified the variables, the last thing that we need to do is we need to identify the optimal lags of the variables. The optimal lags of the variables, right? So there are distributed lag analyses, but one thing that we will do is we'll compute the, where we look at the variable at multiple lags, and we'll do a simple correlation analysis. We will do a simple correlation analysis with the multiple lags, and we'll see which is that lag which gives us the best possible figure, right? Now, having said this, the next question that comes out to us is that how do we do these things? So what are these concepts? What is stationarity? What is co-integration? What is Granger optimal lag? And this is where, this is where you need to have a basic understanding of time series concepts. So these are some of the basic time series models. The basic time series models, or basic time series concepts. Now the question that comes in over here is that how is it that we can look into this in different ways. So let's first of all start by talking about the concepts of stationarity, and let's take two variables and see how is it that, or when is it that this stationarity applies, how do you identify stationarity. And when I talk about identifying stationarity, we'll talk about it in a graphical manner, as well as we'll talk about it in a statistical manner. So what are the statistical tests to check the stationarity? So the first concept that we start off our discussion with is the concept of stationarity. Now, assessing this stationarity is something which is really important. Now, because without stationarity, without ensuring that your model is stationary, you cannot develop the model. And the next thing also that you need to keep in mind is that when I'm talking about stationarity over here, right, I must have sufficient number of records to perform the analysis, right? Because doing stationarity has, or you developing any of the performing these checks requires a minimum of at least the 50 observations. So we require at least 50 observations to develop these models or to perform any of these exercises, right? So a linear regression model can do even without less than 50, but it must have more than 30 records at least. Or even for similar, let's say around 20-25 records, you can also develop the model. So if you are actually collecting annual level data, you need to ensure that you have at least 50 years of data with the bank. And if it's like last 20 years of data, you must have at least quarterly data points. So that is important because the stationarity, co-integration, Ranger, causality test, optimal lag analysis. So they have a minimum data requirement. Otherwise, the results that you get, because in all these measures, like when I talk about these tests, there is another measure which would become very important, because when you develop multiple models and you want to select the best model, or the best model from a set of models, that is where concept like AIC comes into play, or which we call the ACF information criteria, which comes into play. Now with AIC in place, it becomes very difficult for us to take care of this, right? So with AIC in place, AIC requires a minimum of 50 observation to give us an unbiased picture about the information capability of the model, because AIC is inversely related to the residual sum of squares. So higher the residual sum of squares are, lower the residual sum of squares are, lower is the AIC values. So this is something that we have over here. Now, the next question that comes out to us is the following. So the next question that I need to answer over here is that how is it that this model will be, so let's start off with talking about stationarity. What does the stationarity of a time series mean? And for this, the example that we will use is called the example, is that of the gross domestic product. So we'll use the real GDP values or GDP growth rate values, right? Because real GDP is something which is of great interest, and it is obviously the initial pulse of the economy, the real GDP growth rate. Okay, so let's start off talking about the concept of stationarity. So let's say if I have a GDP series, so let me just plot a hypothetical GDP growth rate series. So this is 0. So this is time. And this is GDP growth rate. Put it at percentage GDP. Okay. So this is, as I told you, the long run GDP. The long run GDP, or as I call the average GDP, the long run growth rate. Now let's say this is how the GDP series moves on. Let's say something like this. So if you see this, you will see that all the GDP, the entire GDP series, right, has been fluctuating around the same long run mean, and that over this period of time, the long run behavior of the GDP has not really changed. So over here, you will see that more or less about this line, the fluctuations too have remained unchanged. So over here, this GDP series will be called a stationary series because the GDP of the average is equal to this X bar, or let me put it like this. The long run or the mean GDP. The mean GDP and the standard deviation of GDP right. So this is, let this be called mu and let this be called sigma. So one thing that we can clearly see is that this mu and sigma remains constant. So a time series where the mean and the standard deviation more or less remains unchanged over multiple subsamples, right? So that is called a stationary series, right? So this particular time series that we have over here, so this GDP series is a stationary GDP series. So what it says is that there are temporary fluctuations which are happening, but that is not really impacting the long run behavior of the GDP series, right? So this GDP series is a stationary GDP series. So a time series is said to be stationary when the mean and variance of the time series remains constant over time. So no matter whichever subsamples you take up, right, you will get to see that the mean and the standard deviation remains unchanged. Now, when this happens, it means that this series is marked by the absence of any temporary fluctuations happening in the behavior of the series. So if I coin it another way, it will be that there are no temporary fluctuations. So no temporary fluctuations. Now, what sort of temporary fluctuations am I trying to talk about over here? So one thing that we'll do is we'll incorporate each of these temporary fluctuations and we will see how this series moves on. So over here, there would be three things that we will generally need to look into. First is trend. The second is cyclicality. Now this will be there in the data if you are considering a data over a very long horizon. Because I said that if it's annual data points, then it has to be more than 50 years, right? So there you get to see elements of cyclicality in the GDP figures, because those because there would be downturns coming in and then you have your upturns and so on. So this figure would be there. Trend cyclicality. The third that I have over here will be seasonality. So there is seasonality. Now seasonality will be captured in even smaller vintage of data. Now what does cyclicality and seasonality do? What they do is they incorporate an element of periodicity in the data. So they would make your data look very periodic in nature. So what they specifically do is they add periodicity to your data. Add periodicity to the data. So your data over a period of time will, at times you will have a spike, you will have a fall, you will have a spike, you will have a fall, and this pattern would continue, right? Now the question that comes out over here is that how would the series look like if I had any of these, and why is it that I am saying that each of these work to get towards in making my time series non-stationary in nature? How do they impact the long run behavior of the stationary time series? So first let's start with trend. Now when I talk about trend, I am talking about temporary trends. I am not talking about a permanent trend, right? So over here I'm just talking about the temporary trends. So these are the trends that, so these are trends, you know, which come and stay for a certain period of time and then they tend to drop off. So those are temporary trends. Now when I talk about temporary trends, how would they look like, and how is it that they would make your data non-stationary in nature? So let us look into another time series data, another time series plot. So over here, zero, and this is your time, and this is your percentage GDP. Now let's say I want to draw a straight line, right? So this is the long run GDP again. So the long run GDP is being defined as a constant GDP. So if I take out the series mean over all the 50 years and I find out a mean value, that is the long run mean. Now, how does your time series look like in the presence of a trend? So this is how your time series behaves. Let's say there is a trend which comes in and that impacts the GDP. It starts going up and then gradually again it comes down. Then it goes on like this. Now observe that if I ever wanted to capture this with a single line trend, how would I do it? So up to this point, there is a straight line. Now to approximate this part, my line would look something like this, right? Now, if I want to approximate this part of the behavior, I would see it is something like this. So one thing you can see is that one unique straight line cannot really capture the overall behavior of the series. So if you consider this part of the series, you will get a specific value of mean. Then you plot, if you take up this part, you will get another mean value. So you will get a mu2. And if you look in over here, you will get another mean value, which is mu3. So over here at each stage, mu1, mu2, mu3, you see that the mean is constantly changing, right? So this is what a non-stationary series looks like or would be captured through. Now, if you look into this part where the mean was increasing, right, mu2, this part is a very temporary increase, right? So the increase in the GDP in this part is not always because of some fundamentals or permanent change in the macroeconomic fundamentals of the economy, but it is because of some temporary trend which is falling into it. So that is how this media, so this particular part is to be captured. Now when I am doing this, when I am talking about this particular part, so basically what you can see is that this trend or this trend in the mean which trend in the GDP mean which I was talking about is a very temporary factor, and had it not been a temporary factor, it would have always persisted, and that would have had a permanent impact on the long run mean. But over here this is not the case. This increase or decrease has happened very temporarily, and after a point of time, it has again gone down. So over here what I get to see is mu1, mu2 and mu3 are three separate group means, right? Therefore what I can say is that this change or this variation in the mean is because of some temporary fluctuations, and hence the mean varies over here. Given that the mean varies, the standard deviation in the series will also vary. The mean varies, and therefore the SD will also vary. SD varies, right? So there is mean and there is SD. So each of these series that I have over here are are very important, right? So they are kind of things which are there in place, and so basically what you get to see is that given that this mean varies, right? So there is an element of temporary fluctuation, and it is that temporary fluctuation vis-a-vis which causes the mean and the standard deviation to vary, right? So therefore what happens is Okay. So over here, what you get to see is the following. You have mu1, mu2, mu3, right? So these temporary fluctuations, if it is there in the data, when a temporary trend. So when I am developing my predictions, then I will end up developing erroneous predictions. Yeah. So as I was saying, so talking about the temporary trend, right? So it is this temporary trend which makes my data non-stationary. And therefore, this temporary trend cannot be incorporated in the model if I am trying to make any prediction. So this is what is the concept of non-stationarity. So a non-stationary time series is one. So non-stationary time series is one where there are temporary fluctuations, and this and trend and temporary trend is one of the cases which leads you to non-stationarity. So this needs to be treated before you develop any kind of statistical models, right? Now let's come to seasonality. The seasonality and cyclicality would give you similar kind of graphs. It's just that the element of periodicity for the two will be very different, right? So So let's look into the third picture, the third graph. Yeah, am I audible now? Can you hear me? Okay. So as I was saying, that this time is there, and I have my percentage GDP also there. GDP growth over there, and this is the straight line, the long run straight line that I have, or the long run growth. Now, if there is an element of seasonality, it will happen something like this.
Hello. Hello.
Okay, am I audible now? Can you hear me? Perfect. Okay, so as I was saying, that yes, so over here if you have a look, so we were talking about seasonality, right? So if you have a look, you will see that approximately at a regular interval there has been a peak in the series. So this gives you an element of a temporary element of spike or a fall. Right now if I am trying to predict any time series or trying to make any time series prediction with this, right, that's where you will get to see that that this acts as a temporary addition. So every time I need to do a prediction, I first need to remove these temporary addition, because if these temporary troughs are, I mean these temporary peaks or due to seasonal impacts are there in the series, right, then when I am predicting these periods, right, there I would end up over predicting them, right? So whenever I am doing any prediction, my prediction needs to be a stable prediction, and hence what I'll do is I'll remove all these temporary components from there, and in a sense then do my model predictions, right? So that is something what the overall idea is. So seasonality adds an element of temporary periodicity. So basically if you consider this subset, right, and you consider this subset, so in these two subsets of the same data you will come across two separate means. So again in the presence of seasonality what you can see is that the mean varies from one point to another point, right? So from one subgroup to another subgroup to another subgroup. Now when it moves across the various subgroups, So as you move from one subgroup to another subgroup, what you get to see is that the mean keeps on varying, right? So so this element of seasonality is also something which is this element of seasonality is a temporary element or adds a certain element of temporary behavior to the data and hence needs to be treated. So this is another element which causes non-stationarity in the behavior of the variables. So these are the three key components because of which a stationarity arises. And rather, let me put it this way, that these are the three components which creates non-stationarity and can be adequately treated, right? Now, if it is something else, so if you think about it in another way, so there is another component of it which is sudden erratic fluctuations. Now, if there is an element of erratic fluctuation, then you cannot do anything about it, right? So you cannot do anything about it in the sense that so we cannot do anything about it because that cannot be predicted. Now, if there is a sudden sudden flood or a sudden natural calamity, we cannot control for that. So that is beyond our control. So what we can control in our analysis are these three components. So what we need to understand is that how is it that a series gets detrended, or how is it that a typical series can be deseasonalized? So that's the next question. So before we move into talk about this, so I would take a pause and I would ask if there are any questions. I'll take them up and then I'll move forward. So do you have any questions? Just read through this for a minute and then we'll get started. Okay, so any queries up to this point? Fine. So let's move ahead. Now, over here, the question that comes out is that how do I detrend a series? How do I deseasonalize a series? And how do I kind of, so how do I, or how would I capture this mathematically and how do I test it statistically? What are the different ways of doing this, right? So basically, first of all, then let's characterize a time series and let's see how is it that a non-stationary time series would look like. How would you identify whether a series is non-stationary and what tests would you do? So over here, we are going to talk about two very famous tests that has been proposed in the history of time series, and one of them is a simple Dickey-Fuller test. It's a Dickey-Fuller test, or as we call it, a DF test, right? A Dickey-Fuller test, or as we call it, the DF test. And there is another test which is called the augmented Dickey-Fuller test.
Sir, in Python, there are functions for Dickey-Fuller, but in SAS, can you please help me out because I don't know. In
Yeah,
SAS, how
so
do we do
similar.
that?
Yeah, so in SAS when we use the proc arima, the arima procedure, over there exists an option called ADF. So if you put in that option, you will get the augmented Dickey-Fuller test.
Okay, sure.
Yeah, I'll be next showing you how to do this. So I need to talk about the ACF and the PACF first, and once I'm done with that, I'll show you how to do this test in SAS. So obviously, yes, there's this Dickey-Fuller test and this augmented Dickey-Fuller test. So now the question that comes out is that why or how do these two tests work? Now to define these tests, right, we need to define something called a AR process or an autoregressive process. Called an autoregressive process. So what is an autoregressive process that we are talking about? So an autoregressive process is nothing but it is a process where the value of the time series in today's point of time, at this present point of time, is a function of the value at t minus 1.
So why we do auto-regressive process?
I'm coming to that. So basically, when we characterize any time series models are broadly of two types. One is the AR process or the autoregressive process, where we say that the yt, the value of y, or the variable at time t, is a function of its value in the previous or the historic periods. So that's autoregressive. And the second part is the moving average process, where we say that the value of y at time t is a function of the historic shocks or the historic error terms. So that is yt minus. So those are that's the MA or the moving average process. So Dickey-Fuller test is used to, or this particular test is used to explain the stationarity of an autoregressive process, where a particular time series variable, let's say GDP today, will be a function of GDP t minus 1, t minus 2, and like this. So it will keep on going backwards. So that is the point where we would need to look into this, right? So this yt is equal to yt minus 1 plus epsilon t. So this is so this process or this particular equation is known as, so this is a autoregressive model of the order 1, and this regression equation and this equation has a very specific name. It has a very special name. Does anyone know what this is, what this equation, what this AR process is called? So anyone who has worked with time series over here in some other, in any other domains, this particular equation has a very specific name. Okay, so this equation is called, sorry,
Is this ARIMA process?
no, this is an
I
AR
think
process. So this is an autoregressive process, but this specific equation yt equal to yt minus 1 plus et has a very specific name. What is that? So it's an AR process, right?
Yes.
So this is called, so this equation is called the random walk. This is called the random walk. Random walk model. Now, this name of this equation originates from a drunkard's walk. So, if when a drunk person walks on the road, he doesn't have any specific direction, right? So he goes haywire. So sometimes one step front and then one step back. So it says that this yt is impacted by yt minus 1 plus a randomness, where this et is a white noise. And how do you define the white noise? The et is defined as a normal distribution with a mean 0 and a sigma square u. Now this is how the et behaves, right? So the et is a white noise term. So this is the same white noise that we had studied in linear regression, right? Now comes the next question. Why is this called a drunkard's walk or a random walk? So if you just do a very simple iteration over here, let's say at t equal to 0 at the initial point, so y0, okay, so this has nothing to do with your random forest, because random forest is not random at all, but this is a pure random process. Okay, so over here, let's say at t equals to 1, the first time period. Now every time series model has an initial time period which is specified at t equal to 0. So one thing, if you see over here, you will see that y1 will be explained by what? y0 plus the randomness present in time 1. Similarly, at t equals to 2, you will see that this is y2 is equal to y1 plus the randomness in time 2. But this y1 is nothing but y0 plus
explain the
e1.
randomness.
Sorry,
Sir, can you please help us to explain the randomness that
I'm
is
explaining.
given?
Yeah, so I'm explaining the randomness only. So this becomes y0 plus e1 plus e2, and this keeps on continuing. Let's say I start evaluating this for any k periods. So one thing that you can now see is that this yt So yk will be nothing but y0 plus e1 plus e2 up to ek. So at any kth time period, right, it is driven by y0 plus summation 1 to k. Now look into this expression very carefully. So if I interpret this particular equation, it says that the value that y takes at the kth period is explained by the initial condition, so from where it starts, and then by the addition of the error term. So every time the noise process keeps on adding and yk keeps on taking its value. So the key generator of yk in this equation is nothing but this white noise error term, because y0 is a constant value, so it is the value at y equal to 0. So when this error keeps on adding up one after the other, what you get to see is that the noise has kind of magnified, right? So when it is just because of the pure movement of the noise that this entire thing keeps on going around. And hence what you can see is that if this is the time series equation, right, which the variable follows, the entire values are generated, are explained by the error terms. And given that they are explained by the error terms, therefore what should happen is, therefore we call this a random walk, because the value that y takes at any th period is determined by the error, the white noise error, and not by any deterministic values of yt. So the paths at any time, it can be a positive value, it can be a negative value, so whatever it is, so it is determined by random movements, and hence this is called a random walk, right? Now this particular series has two characteristics. Now a random walk series is a typical example of a non-stationary time series, right? So this time series is non-stationary. Why? So if I try to find out the mean of this series, what will be the mean of this series? The mean of this series is the expected value of yk. So y0 is a constant plus summation t expected value of epsilon t. So over here, if you look into this, what we will see is the following: that this expectation of error is 0 because the mean of all the error terms are equal to 0. So this is y equal to, so this is the expected value, which is y0. And what will be the variance of this? The variance of this series is, the variance of this series is yk equals to t dot sigma square e, right? T dot sigma square e. Now if you do the calculation of the variance, you will get this formula. So it is expected value of yk minus the expected value whole square. So y0 cancels out, so this becomes et square, the variance of the sigma square e, and t times this, so it's t sigma square e. Now the question is, so now what is the thing? So over here it is constant in terms of mean. So it is constant in terms of mean, but the variance of this is not constant. Non-constant, right? So over here, the next question that comes out is that that expected value of yk and this. So one thing I can see is that this series is a very typical series of a typical example of a non-stationary series. Now, I may write this series as a very general equation. Now, let's say if I write this, so this series is written something like this: yt is equal to rho yt minus 1 plus et, where et follows a normal distribution. So where et has its conventional specifications in 0 sigma square. Right? So over here, if I need to test whether a time series is stationary or not, what I need to test is that H0 rho equals to 1 versus the alternate hypothesis rho not equals to 1. Or let me put it as mod rho equals to 1 versus mod rho not equals to 1. Because if this null hypothesis is accepted, right? If H0 is accepted, then the series is non-stationary. Non-stationary. So this is the basic test of a stationary versus a non-stationary process, and the very benchmark of a non-stationary process is this random walk process. So this is the point from where your test of non-stationarity begins. So how do we test this? This is tested. This is what the Dickey-Fuller test does. So Dickey-Fuller test is defined like something like this. The estimated value rho hat minus 1 divided by the standard error of rho hat. Now, if this is again, if this satisfies the decision rule, which is if p is less than alpha at 5% level of significance, so then at 5% level of significance, the null alternate hypothesis is accepted or the null is rejected. So this is what we do when we test for non-stationarity, right? But the Dickey-Fuller test had a basic problem. So what was that problem? That it was applicable only to your AR1 processes. So this test had one problem, that it was applicable only to AR1 processes. So that is where the augmented Dickey-Fuller test was introduced, which took into account difference equations or time series equation with multiple lags as well. And the biggest part of the augmented Dickey-Fuller test is that it could use both, could test for both, AR as well as MA processes. So if you have an AR and MA process involved in the equation, it could test the stationarity of both and could finally give you the optimal lag, and it would give you more figures, right? Apart from testing for the significance. So what it would actually tell you is that, okay, which is that lag at which the most significant, up to which the autocorrelation is more significant, and so on. So that is why, the Dickey-Fuller test has been replaced by the augmented Dickey-Fuller test. But the entire idea remains the same on the whole, to test whether each of the coefficients of the K difference equation, K of the K lags, is equal to 1 or not, right? So if you see that there is a coefficient which has 1, you know that the time series equation itself is non-stationary. So that is what we try to do in so that is what we try to do in this particular measure, or in this particular exercise, right? So that's one. The next is the next that we look into is that how is it that this augmented Dickey-Fuller test is done. To perform the augmented Dickey-Fuller test, or to infer using the augmented Dickey-Fuller test. Now, I'm not writing the augmented Dickey-Fuller test statistic. It's a complicated statistic comprising of lags. So just check that out from from Google or from any of the standard textbooks. So I'm just trying to talk about the techniques or the concepts that we use to infer about stationary and non-stationary time series. So basically, when we use the ARIMA procedure, right? So when we use the ARIMA process, it is there that we use the augmented Dickey-Fuller test to infer about the decisions, right? So that is something that we will be kind of talking about. Okay. So inferring about the statistical significance of the of the stationarity process, of whether the C is stationary or non-stationary, using ADF, we use two functions, or we use two graphs, or two plots rather. One is called the ACF plots, that is the autocorrelation function plots, and the second is the PACF plots, or as we call the partial autocorrelation function, right? So this ACF and the PACF plots play a very critical role in helping us decide on the stationarity of a series in a AR process which has multiple lags, or which even has moving averaged components into it, right? So the next thing that we need to understand is how do we read these ACF and the PACF plots, right? So just give me 5 minutes time, guys, and we'll just resume back. So till then, just go through these concepts that we have discussed. Next, I'll talk about what ACF, PACF is, and then we'll see how is it that we can deploy these in SAS. Hey, hi guys. Yeah. So any questions up to this point? Okay, fine. So now the next question that comes out over here is, okay. So now coming to this concept of ACF and PACF. Now ACF stands for the autocorrelation functions, right? Stands for the autocorrelation function. And PACF for the partial autocorrelation function. Now, what does these have, or what implication do they have for stationarity? Okay. Now, let's say there is a, so let's say a series is not non-stationary. Let's say series is a stationary series, right? So then the question that comes out is that how would the ACF autocorrelation function look like? Now, what does this autocorrelation function essentially do over here for us? Now, it helps us look into the correlation between two lags. Correlation between two lags, right? Now it can be between lag 1 and lag 2, lag 0 and lag 1, lag 0, lag 2, lag 0, lag 3, like this. So between two lags. Now which two lags? So it gives you, let's say, between yt and between yt minus k. Now if your series is not typically, if your series is typically a stationary series, so as you go back in time, right, the impact of the historical lag will reduce on your TH period or on your current value. Let's say if I have 50 years of data, the impact of t minus 50 on t will be the minimum, or will be the least, if it is a non-stationary series. Now, if it is, if it's a stationary series, so the impact of the t minus 1th lag on yt should be the highest, and that should be the most important, the most significant lag. So that is where, this autocorrelation function becomes important in helping us assess the concept of stationarity. Now, if we see that any distant historical lag at a given intervals is impacting the YT, then you know that that series is a non-stationary series. So the question is, how would the ACF for a stationary series look like, right? So let's first look into that. So let's say, how would the ACF or the autocorrelation function of a stationary series look like? So let's have a quick look. So this is 0, this is +1, so that's the highest value that a correlation coefficient can take, and this is -1. So +1 is a perfect positive correlation, and a -1 is a perfect negative correlation, and 0 is 0, right? Now let's say, so how would this lag look like? Now this is your lag -1 or 1 lag. This is -2. So this is -3. This is -4. And it continues like this, right? Now let's say it is a very stationary series. Then what would happen? Then the first lag must have the highest correlation. So there must be, so the highest correlation must exist between 0 and -1. And then over successive time period, right, this correlation must gradually kind of go down. Right? So if you see that the correlation function or the autocorrelation values are falling exponentially over the lags, then you know that that series is a stationary series. Because what is happening over here is that given that the series has or is following its average long run average behavior or is fluctuating near its long run average behavior, you would expect that the most recent lags should have the highest autocorrelation with the 0th lag. And as you move ahead and you start going back with the lags, you will see that the autocorrelation starts falling. And this is precisely the identification of a stationary time series, right? So how would you define this case? So if a time series is a stationary time series, its ACF would exponentially decay over the lags. The ACF would exponentially decay. exponentially decay over the lags. Exponentially decay over the lags, right? Now, the next question that comes out is, then how would the ACF of a non-stationary series look like? And how do I identify the type of non-stationarity which is there, right? So, it would look something like this. Okay. So now let's say so over here, if you have a look into this autocorrelation function, right? Now, what does this tell you about the series? Now, first of all, the thing that we get to see here is that there is no specific pattern to this autocorrelation, right? So it means that there are some components. So there is something because of which the autocorrelation between these two lags is pretty high. Then that component is missing when I want to study the autocorrelation lag between 0 and 2. Again, in the third point, I want to assess the autocorrelation between the 0th lag and the third lag. I again get to see that component because of which the element of autocorrelation is high as the first lag is also in the third lag. So it says that there is some element, there is something which is there in the autocorrelation plots, right, which is present there, and it is this autocorrelation plot which makes this, which helps, and it is this temporary elements in between which is causing the time series to be non-stationary, and because it is present sometimes and not present other times, this component which is creating this time series to fluctuate are temporary factors. They are not present unanimously throughout at each and every point. Right now, if they are temporary, then they need to be removed before I take up any other for any further analysis, right? So this is how your non-stationarity would look like. So in contrast to the ACF of a stationary series, the ACF does not decay over distant lags. ACF does not decay. Does not decay over extensive lags. Right? Are we clear on this? So any questions up to this point?
So you said ACF doesn't decay with extensive lags, but in the left hand side there is a graph that there is a decay, extensive decay in the ACF. So can you please help me out because there is some confusion in it.
So what is confusing you about all this? This is what I was explaining over the last half an hour.
Sir, in the left hand side there is a graph where it's a steep decay in the
Yeah,
steep
why is
decay
it
in the
decaying? Why is it decaying over the on the left hand side? But why is it not decaying on the right hand side?
Tanmay was just explaining like what are the how would the two graphs look like in case of a stationary time series and in case of a non-stationary time series. So the left hand side, which is showing ACF is having a exponentially decay over the
Right.
lag, so that means
So
that's a
this
pattern
is for the
to it.
case of a stationary time series. Exactly the version. So this is for the stationary time point. I mean for a stationary time series. So when a series is a stationary time series, the ACF would exponentially decay over the lags. And over here, if ACF does not decay over the extensive lags, that is the case of a non-stationary time series.
Oh, okay, sir. Okay, thanks a lot. Thanks.
Okay. Okay, and out of the non-stationary case, there will be another typical observation. So -1, -2, -3, -4. So let's say So let's say this is -1 lag, -2. But again, in the -3 lag, this is somewhere like this. Then this is like this. Then in -5th lag again, you see again it spikes up. So one thing that you can see again over here is that this spike which has happened very periodically, right? At every alternate period this spikes up. So this gives you an idea about a cyclicality in the data or some kind of a seasonality in the data. Let's say if it's a matter of a season, let's say it spikes up every 12 months. If it matter or a matter of every 6 months, right? It's every 24 months. So if it's a season, it would repeat itself after every 12 months. So if you generally see a spike happening in the ACF function over at a period of every 12 months, right? Every 12 period where the data is 12 months, then you know that there is an element of seasonality involved into it, right? So to have a season, to capture seasonality, you generally need to have a monthly data. So this is where the concept of seasonality comes into the model, right? So this is the next type of stationarity issue that we have in the data. So by looking into the ACF or the autocorrelation functions, I should be able to identify, whether the series is stationary or non-stationary. Now, if you look into the PACF functions, right, in the ACF functions, the autocorrelation functions, right? So then by looking into that, what you can clearly state is that yes, whether this is a stationary series or not, right? Now if it is not a stationary series, then the next thing that we'll talk about over here is that how is it that it can be made stationary. Now the next thing that we'll talk about over here is that how is it that hello, am I audible?
Yes, sir.
Okay. Okay. So when we are trying to do, when we're trying to test for stationarity, right? So over there, so we are using the PROC ARIMA, the ARIMA procedure. So ARIMA stands for AutoRegressive Integrated Moving Average Method, and this ACF and PACF is generated as a result of the ARIMA procedure, right? And within there is an option called the ADF test, which is ADF, which generates the result of the augmented Dickey-Fuller test, right? So in the next class, so tomorrow when we start off our discussions, tomorrow, we will start